What's going on, guys? Got another amplifier on the bench currently. This amp was given to me in a trade. It is a Fender 212 Deville. The previous owner said that he was had it cranked and that he was playing pretty loud, and the amplifier just quit on him. So I'm suspecting off the bat just a blown fuse, but we're gonna have to kind of dive in to see what actually tripped that fuse. If you have an amplifier that you know is blowing fuses, it's going to be a good idea to plug the amplifier into a current limiter. If when you turn on that amp, if there's a short to chassis or any other problem that's drawing an excessive amount of current, this current limiter should glow brightly and let you know that there's a problem. All right, we've got our amplifier plugged into the current limiter, and we're going to attempt to turn it on. Right off the bat, we get nothing, so I'm going to check the fuse in the back. So I've taken the back off the amplifier. We can access the fuse here. You don't need to take off the back for that, but I went ahead and took it off because I want to look for any possible points of failure that may have given an indication of why that fuse has actually blown. It's at this point that if you're not sure what you're doing, or you've never worked on tube amps before, this is the stuff that you really don't want to touch. These up here are your filter capacitors. They can hold a very large charge even after the amplifier is turned off. There's another guy right here. So even after the amplifier is turned off, it is still not safe to touch. So you can be seriously injured if you mishandle this. I will show you how to discharge these capacitors safely. So if you do want to work on your tube amp, hopefully you can do that while being safe at the same time. This is what I use to discharge the capacitors. It's a simple resistor that's connected to an alligator clip, and we'll take this lead over here, clip it to the chassis, and what I'll do is touch the positive ends of the capacitor, and when I do this, I don't want to touch anything else. So I don't want to come over here and accidentally touch that screw, for example, while I'm touching that capacitor. I'll do my best. I'm a little shaky because I've got the camera in the other hand here. The purpose of the resistor is to limit the amount of voltage going to chassis, and basically all we're doing is draining the filter capacitors of their remaining charge. I'll come up here and do the negative ends. I'm always in a position where I think I've done something wrong, so I'll go through and usually double, triple, quadruple check everything that I do. At this point, you could take a multimeter and double check the remaining charge just to be sure as well. So I've got a multimeter here. We're set to direct current volts. Right now, obviously, we have a reading of 0. I've got my negative lead hooked to chassis, and I'll come up here and I'll take a measurement from one of the filter capacitors. You can see even after I drained the filter capacitors, it still has a residual charge on it. If I release the connection from the capacitor, you can see it goes down. I'll touch another one, and I'll go through and just touch them all. Again, I'm always assuming that I'm doing something wrong, and we're going to try to do this safely. I'm just going through and checking my readings here. So we're less than 1 volt here, so this amp should be safe to work on at this point. So come over and grab this fuse here, and we'll take a look at it. Right now this looks like it's a good fuse. But to double check, we're actually going to take a continuity reading of that guy. Typically when they blow, it actually looks something like this. You can see the char mark. So this is really what we'll see when it blows. But we're going to do a continuity check on this other one just to make sure. So I've got the multimeter set to our continuity setting. It looks like a little sound wave, and that simply means when you put these two together, it'll emit a beep indicating that there is continuity. This is going to be interesting to see if I can do with one hand. Alright, so we're going to take a look at this known blown fuse, and we're actually just going to touch the contacts there to the multimeter probes. You can see not much activity is happening. The OL stands for over limit, so we do not have continuity, obviously, in this blown fuse. Now let's take this known good one and see what kind of activity we get. So right off the bat, we've got that beeping sound indicating that there is continuity within that fuse. Alright, so this is the fuse that came out of the Deville. We're still in continuity settings. I'm going to touch the fuse to the leads. You can hear that beep sound isn't occurring. So even though this fuse looks good, it's been blown to the point where we can't see it. So I'm going to throw a new fuse in the Deville, and we're going to see if we can get it to fire up. The new fuse is installed into the amplifier. Again, we are plugged into the current limiter, and we're going to see if this guy will fire up. Alright, so we've got power, and the current limiter is not being engaged. So I've dimmed the lights just so I could see the heaters. It looks like we've got the heaters working correctly in all these tubes. If the current limiter engaged as soon as I turned on this amp, I would pull all the tubes and then start inserting them one at a time, starting with the preamp tubes, going over to the power amp tubes. That would help kind of narrow down which section of the amp was malfunctioning. Now really my first step after discharging the capacitors would actually to be a visual inspection of the components to see if there's any resistors burned, or filter capacitors or electrolytics that's starting to leak and bubble. I know these guys, when they go bad, they'll kind of blister or bubble here, and then with our resistors, usually we can see like a scorch mark on it. Prior to making this video, I did just that actually, so I actually know off the bat something that's wrong. I'll see if I can get it in here. If you guys can see this resistor here, I'm going to try to get some more light on that here in a second. And then there's this resistor there as well. Those are blown. I think I got a better shot of it here. You can see, I don't know if how well you're going to be able to see that, but definite scorch marks on there. And then this guy as well. And you can actually see that scorch mark on the other side as well. So that's what I actually looked at, and then which brought me underneath to find that. I don't know if this one had that same scorch mark. There might be a little bit of it right there. But anyway, so yeah, those are going to have to definitely be changed out. So the only good thing, in my opinion, about PCB boards as opposed to the vintage style of amplifiers, the hand-wired, is the ease of serviceability when it comes to the actual schematic. This is a layout up here. This is your schematic for the Deville. The only thing that's kind of handy is this numbering system here. Here's our small board, and here on R61 and R62, those can easily be identified as the blown resistors. These resistors were very close to the output section of the amplifier. Here's our two output tubes, and we can see R61 and R62 is connected to the screen grids of those tubes. So those are our blown screen grid resistors. So I've kind of explained how a tube works in a separate video, but I'll give you a quick rundown how this power tube works real quick. Alright, so we got all these pins that connect to these different elements inside. Here on the left is kind of a list showing you the pinouts, what component is tied to which pin. So we can start with the heater. The heater is what's responsible to heat up pin 8, which is your cathode. Now once that cathode gets hot enough, it starts to throw off negatively charged electrons that is attracted to pin 3, or the plate which is connected to pin 3. So we throw a high amount of direct positive current to the plate, and then we've got this cathode throwing off negatively charged electrons that's wanting to go through the plate and out the wire of pin 3. Here at pin 5 is our control grid, is what actually regulates the amount of current going through this tube that it would equate to your amplified guitar signal. Before your signal hits pin 5, it's going to go through a series of preamp tubes, and then a phase inverter if it's a double-ended amp, and then this, when you strum your guitar, basically your pickups are creating a alternating current, a positive and then a negative, positive and negative. And so since these electrons coming off the cathode are negative, when your signal comes in its positive state, it allows that current of electrons to flow, and then when your guitar is in its negative state, it charges that screen grid negatively. Since these electrons coming off the cathode are negative as well, that screen grid is going to be the first thing that they encounter. So if we have negative electrons first meeting a negatively charged grid, it will repel and impede the flow of current through that tube. In a nutshell, that's how a basic preamp tube works, but this is a power amp tube, and so we've got a couple more components. Here on pin 4 is what's called a screen grid. Like I said before, we had a large amount of direct positive current being supplied to this plate. Well, we're kind of doing the same thing to this screen grid. Let's say if there's, I don't know, 425 volts on that of direct current, positive direct current onto that plate, we might throw 400 volts onto the screen grid. That, in effect, when your guitar signal comes in as positive, it allows the electrons to pass through that control grid, and then after that it sees this screen grid, which is also positively charged. So think of it as almost a turbocharging of the tube. So it accelerates even faster at that point. Next in line, we have our suppressor grid. The purpose of that is to kind of play cleanup with the electrons. Since the electrons are moving so fast, it hits our screen grid, which turbocharges them, and then it's wanting to go to that positive plate. A lot of times those electrons will kind of bounce off that plate and kind of wreak havoc in here, causing issues. Since that suppressor grid is connected to cathode, it's going to be a more negatively charged screen. And so let's say we have an electron that comes through here, it bounces off the plate, and rather than bouncing all over the place, it's going to see that a negative charge here and want to be attracted back into the plate. So it's almost like playing cleanup. So if we go back to the screen grid here, our resistors burnt on this, so we don't have positive voltage going to that screen grid. So what we've done is interrupt the expected flow of how this tube was designed. So there's electrons kind of bouncing all over the place, and it's going to cause a lot of issues. So we need to remedy that by replacing those resistors. I actually figured I'd fire this thing up. The screen resistors are blown, but I wanted to allow you guys to hear what the effect of a blown screen resistor would be on a tube amplifier. I'm on the clean channel. I'm about 2.5 on the volume. Again, I'm on the clean channel, so we shouldn't be getting much of any breakup, especially at 2.5. So. So like right there, when it gets kind of chunky. Especially this big fat low chord. Look at big old G. Sounds like we're on the drive channel right now. So it's breaking up really early. So I'm gonna hopefully there won't be that hard of a repair. I'm actually going to try to do this repair without removing the board, and I'll show you that what that looks like here in a sec. So to get the board out, it's a series of screws here. There's a bunch of 4, 5, 6, 7, 8, 9 of them, and to get to these back ones really far in the back, we actually got to take the main board out. Now to get the main board out, we've got to take off all these knobs and then the nuts holding them, and then kind of wiggle this guy out. I did a mod on a 410 Deville, and it was not fun fishing this board out, and these ribbon cables here are really prone to failure once you start bending the board back and forth. So I'm not wanting to do any more damage. Let's see if I can get you a better view. Here's one of the blown resistors here. Since it's so close to the edge, I bet you I could desolder these guys, pre-bend my leads, and with a pair of pliers or something, a needle nose pair of pliers, fish that resistor up there, and then bend one of the leads, and then get it into place. I bet you I could do that with both of them. So rather than just replacing the screen grids, it'd be in our best interest to address actually what made them fail, and so it doesn't happen again. Now, from what I understand, the most common cause of blowing screen resistors is shorted tubes or tubes that are failing. Even though we played through this, a small amount of vibration could cause a short in one of these tubes that could take the screen resistors out with them. Now, like I said, the previous owner did say he was playing rather loud, and so who knows what kind of vibrations these guys were seeing at the time. So in short, I think once we do replace the screen grids, I'll go ahead and throw a new pair of power tubes in there as well. I'm going to start by removing this first screen resistor here. I like to use the solder wick on the PCB boards rather than the solder sucker. So we're going to get this guy out and check back in here in a sec. At this point, the amplifier is unplugged, and I've discharged all my filter capacitors.
Alright, so I've gotten the solder off these leads here using the solder wick. I like using this because those, I don't know if you can see those pads in there. Those are really easy to lift, and so when you use the solder wick, it kind of acts like a heat sink, drawing the heat up the length of the chem wick rather than putting it onto the PCB board. The other thing that's worth noting is that when you use chem wick on a PCB board, when you're soaking up the solder with the soldering iron, to remove the soldering iron and the chem wick at the same time. I know back earlier when I was starting to work on this stuff, I would remove the soldering iron, and then I would be left with this chem wick still soldered to the pad, and at that point when you pull it off, that pad comes off with it, and you've got to deal with a repair. Now if that does happen and you've lifted a pad, what you can actually do, you see that you can follow the trace here now. It's covered with coating. What you can do is take an X-Acto knife, kind of scratch away that coating. Let's say I lifted this pad here. I could scratch away that coating to expose the metal that runs the length of that trace lead there. And then that would give me something to actually solder that resistor to. So I could come off here and maybe do a length of solder to here that would continue on out. So you can repair it. It is not fun to do. I have done it before. Also, rather than bending these leads, you can see it's kind of curved over there. Rather than trying to bend these guys back with a screwdriver or something, which may scratch the PCB board, and it may break continuity with one of these traces. I'm just gonna snip it under here and then pull it out, and then that piece that's above there should come out pretty easily. You can usually, once you have all the solder off, you can kind of just put a little pressure on these leads, and you should hear them pop, and then you can see now it's loose and it's ready to kind of fall out. So we're going to cut here and then push out the remaining bits once I've cut it. At that point, be sure to locate and remove this small piece from the chassis if it happens to fall down there. Screening resistors out. Here was the holes for it on that tube, and then right here and here was the other. You can see there's a little bit of residue left, so I think I'm going to take some 99% alcohol with a cotton swab just to clean that up real quick. Alright, just got them cleaned up. You can see they look a lot better. So I got my multimeter in ohms. I've actually got, I'm going to go ahead and just test these for the heck of it. I got the positive on one side, the negative on the other. It doesn't matter the orientation with resistors. We actually get a reading here of 464.5 ohms, and you can see this guy just looks burnt to a crisp. And we reference our schematic. Let's see if I can get it on here. It is supposed to be a 470 ohm resistor. So this is at 464.6. And even though it almost blew, it held in there. And these are 1 watt resistors. So this one actually survived. So I've got my multimeter in ohms still. We connected the other one, and this guy is showing the over limit symbol, which means that this guy did fail, and it did take this guy with it. So we found the culprit here, and so we'll just replace it with another 470 ohm resistor. So for the replacements, I'm just going to use a different set of 470 ohm resistors. These are actually 2 watt resistors as opposed to the original.
which was 1 watt. You can see the difference in size there. So we're kind of overbuilding this section of the amplifier. So if this happens again, these screen grid resistors hopefully won't blow. So the first thing I'm actually going to do is take this pair of smooth jaw pliers and run them down the length of each side of the resistor leads, and then that way, once I place this resistor back into the holes, I can bend my leads at 90-degree angles, and we can actually just have it be really nice and uniform on the PCB board. So once I have one lead kind of bent, I can take it up here and put it into one of the holes, and then I can kind of see exactly where I'm going to need to bend the second one. So I'll put a pair of pliers right there, take it out, and then bend right where I need to. And so hopefully once that's done, it'll sit real snug in there. And I'm just doing this on this side so I can get my leads cut in the right spot, and then we'll come in from underneath and put it in how it's supposed to go. So I've got the leads bent into position. You can see that kind of just drops right in there. And so what I'll do is just snip this, flip it around, and bring it up from the bottom. That way we can solder them to those pads there. Alright, so the new resistor is in, and I've got the leads bent over. We'll do the same for this side, and once we get done, we'll go ahead and solder them in there. Now that these guys are soldered back in, I'm going to take some alcohol to them to remove some of the residue. We'll clip the leads, and at that point we'll replace these power tubes, and then take some measurements on voltages, and then we'll run a guitar through it to see how she's doing at that point. Alright, the leads have been clipped, the residue has been cleaned off, and a new set of JJ power tubes have been installed. So I think at this point we're going to turn it on and take some measurements. So once I get the amp on, I'm going to take a measurement on pin 3 of the plate, and then pin 4 of the screen grid, and compare that to the schematic just to make sure we're within tolerance there. We're going to need the plate voltage anyway, so that we can set the bias in this amp. So I don't know if you guys can see this, but right here is the notch for the power tubes. That notch corresponds with that notch right there. So that should be 1, 2, and 3, and 4 going clockwise like that. So it should be pin 1, 2, 3, so on and so forth. So that's how we're going to get our measurements. And I'm not actually going to not attempt to do this with a phone in my hand. We're dealing probably with around 400 volts on the plates, and we're going to try to be as safe as we can. Alright, looks like everything's looking good. The plates on the outers was 434, screen was 432, and then that mirrored the inner tube set. So I think at this point we'll go ahead and attempt to bias this amplifier and do a sound test. So something that's really handy is an online bias calculator. You just pick your tube into your plate voltage. For my case, it was 434, and then we're on class AB fixed biased, and so it gives us our range of bias options. We can do cool, average, or hot. And right now, these are the figures that we're going to try to remember: 34, 41, and 48. We can come over to the actual layout and look for our bias test point. They're calling for, let's scroll up real quick. They are calling for, right there, 60 millivolts on that test point. So this configuration has a common cathode, so that 60 millivolt is for the average of both. So what this actually means is that 30 is what each tube is seeing.
So as you can see that they're biasing rather cold. So when we do our calculations, depending on what we're looking for, we're going to remember to divide the number that we read in millivolts at that test point and divide it by 2, and then that will give us the average of what each tube is seeing. Alright, so I got my multimeter set to millivolts. The bias test point is this guy on the very end, so we'll just take a reading. And looks like we're getting around 43. If we divide that number by 2, you're right around 22 milliamps per tube. And so we're just under 50% cool here. So what I'm going to do is we're going to come over here to this little blue pot, and we're going to adjust that until we can get our reading a little closer to 50% at least. We're going to see what these tubes can actually bias to. Alright, it looks like the most amount of milliamps that I can get to go through these tubes is about 57. We're maxed out here on our bias pot, and so that would give us a reading of about 28.5, which is a little under 50%, but since that's what I can get out of these tubes, we're going to go ahead and leave it. So this is going to be biased a little cool. So all in all, we've discovered that the screen grid resistors were blown, possibly due to a tube failure. We've since replaced the resistors. We've taken some measurements on the plate and screen voltage and replaced the power tubes with new JJ Electronics tubes. We've then biased the amp as hot as we can get it. It's just under 50% dissipation. And so I think at this point everything's looking good. We'll go ahead and do a sound test. So on the clean channel, I might be on 1 or 2. So everything's sounding pretty good. Let's have a little fun. We'll bring it up just a little bit. A little more. So everything's sounding pretty good. We can go over to the drive channel. Sounding great. Let's go to the more drive channel. Everything's sounding great. Just as an example here, like I said, we're biased about as hot as we can get, just under 50% dissipation. If we back this off, that bias pot, we can hear what a super cool bias setting sounds like. So we're on the drive channel. Let's change that back to the hotter bias setting. It just sounds a little bit more full, a little bit more creamy and rich. So I'm liking it where it's at. We're going to go ahead and reassemble, and that should be it for this video. So thanks for watching.